In this video, we solve problem 14.7.015 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use cylindrical coordinates to find the volume of the solid. And we're told that the solid is that inside both the sphere given by x squared plus y squared plus z squared equals 16. And this cylinder given by the equation x minus 2 quantity squared plus y squared equals 4. So the first thing that I would do is sketch the solid as well as I can. The sphere is relatively easy. Got x squared plus y squared plus z squared equals 16. Now I'm comparing that to the equation x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. X naught, y naught, z naught is the center of our sphere because we're not subtracting anything from the x, y, or z. Our x naught, y naught, z naught is 0, 0, 0. So we've got a sphere centered at the origin, and the radius squared is 16. So that means that the radius is the square root of 16, or 4. So over here in three-dimensional space, I'm going to sketch a sphere of radius 4. The way I tend to sketch that is to just draw a circle. And then I add another line for dimension. Okay, so we're inside that sphere. And we're also inside the cylinder defined by this. Now I can tell that it's a cylinder because there's no z in that equation. When I see that equation, I think of a circle in the XY plane. So I think what I'll do is I'll sketch the circle in the XY plane where that cylinder intersects the XY plane, or z equals 0. And then we'll think about, well, what that would look like if z were free to be anything. So this is what we have. And similar to this, we're comparing this to the equation x minus x naught squared plus y minus y naught squared equals r squared. X naught and y naught are the numbers that we're subtracting from x and y here. So the center of this circle is 2, 0. The radius squared is 4. So r equals the square root of 4, or 2. So I've got a circle centered at x equals 0, oops, or x equals 2, y equals 0, and it has a radius of 2. So if that's my center, and this is my radius, I'm going to go 2 units to the left and 2 units to the right, up 2 units, and down 2 units. So that's the cross section or the trace of that cylinder in the XY plane. Notice that it's offset. It's not centered on the origin, but it's centered at 2, 0 on the X axis. But Z is free to be anything. So if Z is free to be anything, what we would see over here is this. We would have a circle down here in the XY plane. And then that would come up to the sphere and intersect at something like that. It's a little bit difficult to draw. It's very difficult for me to draw. So we're saying, okay, we want the solid region that we're interested in is inside that cylinder, but also inside the sphere. And that cylinder is going to go all the way down as well. It's going to go beyond that sphere. The solid region Q is inside the sphere only. So this is Q. All right, now, because we are dealing with a sphere, or a part of a sphere inside a cylinder, we could use spherical coordinates or cylindrical coordinates, but we're asked to use cylindrical coordinates to find the volume of the solid. So we know that our volume will be the triple integral over Q of dV. And in cylindrical coordinates, dV is r times dz dr d theta. We just need to find the appropriate bounds for z in terms of r and theta, the appropriate bounds for r, and the appropriate bounds for theta. It's actually pretty easy. Okay, now when I'm finding my bounds for z, all I do is I look at this surface and I think about the bottom function here and the top function. Well, the bottom function is just the bottom half of that sphere. The top function is the top half of that sphere. So we'll just take this equation and solve it for z, and that's actually going to get us both the bottom function and the top function. So from here, I'll have z squared equals 16 minus x squared minus y squared if I subtract the x squared and y squared from both sides. And then to get z by itself, we're going to take the square root, and don't forget your plus or minus. The positive square root is our upper bound for z. It's the top half of the sphere. The negative square root is our lower bound for z. That's the bottom half of the sphere. Now we want to go to cylindrical coordinates. So I want to write these bounds in terms of r and theta rather than in terms of x and y. Which is easy enough to do. I'll just factor out that -1 inside the radical. So 16 minus the quantity x squared plus y squared under that radical. And remember, in cylindrical coordinates, x squared plus y squared is r squared. So this is the negative square root of 16 minus r squared and the positive square root of 16 minus r squared. So those are our bounds for z. And we also need bounds for r and theta. Now there are lots of different ways to describe the range of values for theta that would allow us to trace out this circle. But I prefer to use a geometric approach. This circle is tangent to the y-axis. It starts sort of on the negative y-axis and ends on the positive y-axis. Thinking of an angle that sweeps from the negative x-axis, or excuse me, from the negative y-axis to the positive y-axis, I'm going to say that my theta goes from negative pi over 2 to pi over 2. And that will work. So those are my bounds for theta. While r starts at 0, so r equals 0 is the origin, and it goes out to this curve. So all I really need to do is find the value for r, or the equation for r that describes this circle. That's easy enough to do. We have this equation of the circle in rectangular coordinates. I just need to write it in polar coordinates or cylindrical coordinates instead. So what I would recommend you do, because x squared plus y squared equals r squared, is to write this twice in FOIL. X minus 2 times x minus 2 turns out to be x squared minus 4x plus 4. You can subtract the 4 from both sides and add the 4x to both sides. So now I've got x squared plus y squared equals 4x. Now x squared plus y squared is equal to r squared, and x is equal to r cosine of theta. So this is r squared equals 4 times r times cosine of theta in general. Now, typically I wouldn't divide out a variable. I wouldn't divide both sides by r to get r by itself. But this time, r equals 0 is actually, or that origin, that point is actually captured by the equation that results after we divide out the r. So I can divide out the r this time, and I will find from here that r is equal to 4 times cosine of theta. And again, the reason I can do that is because if theta equals, say, pi over 2, then r would equal 0. And so I'm not going to miss that origin by writing the equation this way as opposed to writing it this way. So So that is our upper bound for R. And that's enough. So we basically use the equations of the sphere to get the upper and lower bound for Z. And then we use the equation of the circle and our graph of that circle in the XY plane. It's actually really a disk because we're talking about the interior of that to infer the bounds for theta and R. And once we've got the bounds for theta and R and our bounds for Z, we'll just use that to set up the volume integral. Theta goes from negative pi over 2 to pi over 2, while R goes from 0 to 4 cosine of theta. And Z goes from the negative square root of 16 minus R squared to the positive square root of 16 minus R squared. And then the dV was R times dr d theta times dz. Now we're going to start on the inside and work our way out, anti-differentiating with respect to the variable that's there. The antiderivative of Z with respect, or of R with respect to Z, is just R times Z because R is just constant with respect to Z. And then we evaluate from Z equals the negative square root of 16 minus R squared to Z equals the positive square root of 16 minus R squared. So at the upper bound, we'll get this. At the lower bound, we're going to get exactly the same thing, but with an opposite sign. And we're subtracting that negative expression. Actually, I'll write it out. So I'm subtracting R times Z, which is going to be negative R times the square root of 16 minus R squared. But subtracting something negative is the same as adding. So I actually have 2 copies of that. And now we just have this double integral to evaluate. And we continue, we start on the inside and we work our way out. The inside function is 16 minus R squared. The derivative of that is negative 2R. So du is negative 2R dr. Multiply both sides by negative 1. This is a u to the 1/2 power two r dr is negative 1 times du. And since this is now an integral in terms of u, we need new bounds. So I will evaluate u at the upper bound for r and the lower bound for r and simplify. The lower bound is relatively easy, just get 16. The upper bound is more involved. If r is 4 cosine of theta, we end up with 16 minus 16 cosine squared theta. And that is 16 times the quantity 1 minus cosine squared. 1 minus cosine squared is sine squared, the same angle. All right, so that's what we have right here. It's our new upper bound. So now we will anti-differentiate. Bring the negative down, add 1 to the exponent, divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Then we evaluate from u equals 16 to u equals 16 times sine squared theta. And if you want, you could factor out that negative 2/3. So I've got just u to the 3/2 evaluated at this. Now, any number raised to the 3/2 power is that number to the first times that number to the 1/2, or that number times the square root of that number. It's the same thing, just using properties from algebra. So when I see 16 to the 3/2, I think 16 root 16, or 16 times 4, which happens to be 64. Now that's exactly what would happen here. I've got this product raised to the 3/2 power. So I'd raise the 16 to the 3/2, which is going to give me 64. And then I've got sine squared theta to the 3/2. Now we have to be careful about that one. I really want to multiply those exponents and say that that is sine cubed of theta, but this is always going to be positive because I'm taking the square root of something squared and then I'm cubing it. So I really need to think about whether or not this function is going to be positive over this interval. Because when I simplify this, it simplifies to sine cubed of theta as long as sine cubed of theta is positive. So it's actually going to simplify to the absolute value of sine cubed theta because I'm taking the square root of something that has been squared. Square roots are only going to give us positive numbers. So I can factor out the 64 from here, and I think I will. That 64 times that -2 is going to give me a negative 128 out front. And then out over inside here, I've got the absolute value of sine cubed theta minus 1. And I want to look at that sine function. Remember, sine of x looks like this. It repeats itself every 2 pi. So that's negative pi, that's 2 pi, that's negative 2 pi. And we're interested in this function, or the sine function, on the interval from negative pi over 2 to pi over 2. So this is just going to be sine cubed theta whenever sine is positive, and sine is positive on the interval from 0 to pi over 2. So from 0 to pi over 2, we could just replace that with sine cubed. But over here, the absolute value of this is sine cubed, which is going to be a negative number, times -1, which would make it positive. So we have to split this up into 2 integrals. It's not too bad. We can do it. We're going to split this up, the integral from negative pi over 2 to pi over 2 of the absolute value of sine cubed, into 2 integrals. And then we're also going to split this larger integral up into 2 integrals. So let's do that. And then I've got this times the -1, which is going to give me a positive 128 over 3, times the integral from negative pi over 2 to pi over 2 of 1 d theta. This piece is 128 over 3 times theta, evaluated from negative pi over 2 to pi over 2, which is 128 over 3 times pi over 2 minus a negative pi over 2. So that just gives me 128 pi over 3 for this piece. Now I also have to evaluate this piece, and then we'll add them together. Now this is negative 128 over 3 times the sum of 2 integrals. One from negative pi over 2 to 0 of the absolute value of this function. And again, that's going to be just that function when sine is positive. And sine of theta is positive on the interval from 0 to pi over 2. Oops, sorry about that. Somehow video is acting up a little bit today. And then on this interval, sine of theta is negative, so sine cubed is negative. So when we take the absolute value, we've got to multiply by -1. So this is a negative number times a negative number, which makes it positive, which is the absolute value. So in the interval from -pi/2 to 0, we get the negative sine cubed function. And we want to integrate that. And then on the other interval, we want to integrate the positive sine cubed function. Okay, that's the plan. Now, since these are basically the same integral, but one just has a negative sign, the other one has a positive sign, and we've got different bounds, I think it would be helpful to evaluate the integral of sine cubed separately and then use that antiderivative and substitute that antiderivative here. So I'm going to come back to this sheet in just a moment after I evaluate the integral of sine cubed. So I'm thinking of this as just side work. Now that is not u cubed du, because we don't have the du that we need. If u was sine of theta, we would need a cosine of theta as a factor to do the u substitution, and we don't have the cosine of theta as a factor. So what I would recommend doing in this case is this. If you've got sine raised to an odd power, you want to save one of those signs for your du, and you want to let u equal whatever is necessary so that that sine of theta is in its derivative. So I want u to be equal to cosine of theta. Because if I take the derivative of cosine of theta, I get negative sine of theta d theta, and that means I've got negative du equals sine of theta d theta, and that's right there. And if you're saying to yourself, but what about the sine squared? That's not in terms of cosine. That's okay, because we can always write sine in terms of cosine using one of our Pythagorean identities. So we know that sine squared of some angle plus cosine squared of the same angle is equal to 1. So I can find sine squared in terms of cosine squared just by rearranging this equation. By subtracting cosine squared from both sides, I see that sine squared is 1 minus cosine squared, as long as the angles are the same. So this is 1 minus cosine squared, and cosine is our u, so that's going to be a 1 minus u squared. So you've got -1 times 1 minus u squared, which would just give me u squared minus 1 times du. And we can anti-differentiate using the power rule. So add 1 to the exponent, divide by the new exponent. The antiderivative of 1 with respect to u is just u. Then we would normally have a plus c. And in our case, u is cosine of theta. Okay, that's the antiderivative of sine cubed. I'm going to use that here and here to finish my volume problem. So I have -128/3 times the antiderivative of negative sine cubed. So it'll be this function times -1. So I'll have -1/3 cosine cubed theta. This function times -1 is going to be positive cosine of theta. And we're evaluating that from from -pi/2 to 0. And then we want to add the antiderivative of this, which is exactly like this, but with multiplied by -1. So cosine, or 1/3 cosine cubed theta minus cosine of theta. And you want to evaluate that from 0 to pi/2. We want to take all of this and multiply it by that -128/3. And don't forget to add that 128 pi/3 here from here. Okay, so that's the plan. Let's just evaluate now. At 0, cosine is 1. So this will be -1/3 plus 1. And then when we evaluate this expression at pi/2 or negative pi/2, cosine of negative pi/2 is 0. Cosine looks like this. Cosine of negative pi/2 is 0. That's what the graph looks like roughly. Cosine of positive pi/2 is also 0. Cosine of any odd multiple of pi/2 is 0. So this will be 0 and that'll be 0. So we're subtracting 0, which doesn't do much. And then over here, we're going to do something similar. Evaluate at pi over 2. We'll get 0 minus 0, which is 0, minus what we get when we plug in 0. Cosine of 0 is at the top there. That's going to be a 1. So we'll have 1/3 minus 1. All of that is in parentheses multiplying this negative 128 over 3. And we still want to add the 128 pi over 3 that we got from this piece. So we're almost done. Still trying to find volume. Negative 128 over 3. And this is 1 minus 1/3, which is 2/3. And this is 1/3 minus 1, which is negative 2/3. Negative 2/3 times negative 1 is positive 2/3. So I've got 2/3 and 2/3, it's 4/3. And I'm adding 128 pi over 3 to that. So we could go on from here and simplify. I would recommend multiplying by 3 over 3 there so that we can get a common denominator. So I've got 128 times pi times 3 over 9 minus 128 times 4 over 9. Getting that common denominator gives me this. And I see a 128 times 3 and a 128 times 4. So we could factor out that 128. This is 128 times 3 pi minus 4, all divided by 9. And that is the volume inside the sphere and also inside this cylinder that is sort of offset from the origin by 2 units. So please let me know if you have any questions about that. Happy to help you.